Hello all, welcome to this new video lecture on computer graphics. In this video lecture, we are going to cover the topic midpoint algorithm for ellipse. Like in the previous video, you would have seen that we had drawn a circle using the midpoint algorithm. Similarly, in this particular video, we are going to draw an ellipse with the help of midpoint algorithm. So let's get. Now we see that an ellipse is different in shape than a circle. An ellipse is oval in shape, and in circle we know that we just need one radius to plot the entire circle because all the point onto the circumference of the circle is equidistant from the center of the circle. So that equidistance distance is the radius. But in this case, we are going to have more than one radius. That is, we have a major axis and a minor axis. So the major axis is represented by Rx. We also say it call it as A, and minor axis is represented as Ry. We call it as B. So actually the major axis is the entire path. So it is 2 times Rx, and minor axis is this entire y-axis. So it is 2 times Ry, right? So this is the half of it is a semi-minor axis, right? And this is a semi-major axis, Rx. Okay, so now we are going to proceed, but we need to understand that it is different from circle because in circle, two quadrants are kind of symmetric. But in this case, do you see whether this quadrant 1 and quadrant 2 is symmetric? So the answer is no. They are not symmetric. So in this case, we are not going to work with respect to octants, but instead we are going to work with quadrants because yes, the quadrants are symmetric in case of ellipse. So let's proceed and check how it was worked out. And first we'll understand how to make a proper equation of ellipse and how to replace the values of x and y in the equation to understand where the point is lying inside the ellipse, outside the ellipse, or on the ellipse. So let's get started. So now let's see how to convert the equation of an ellipse into a single line. So here we have x square by rx square plus y square by ry square equal to 1. So we'll just multiply square with x square, rx square with y square, and the denominator will become rx square into ry square, which is equivalent to 1. We'll take the denominator to the right hand side and then again bring it to the left hand side by changing the sign of it, that is minus, and this is how we get a equation in one single straight line. Now in here, if I put in the values of x and y, then we can surely get where the point lies on the coordinate system. So if the value comes out equal to 0, it is lying on the ellipse. If it is less than 0, it is inside the ellipse. And if it is greater than 0, it lies outside the ellipse. So now let's see the features of ellipse. In the features of ellipse, you know that it is not here like a circle. In circle, we have 8-way symmetry, so we have 8 octants to represent it. But in ellipse, we have just 4-way symmetry because we can say that the quadrants are symmetric but not the octants. So here we are going to work with respect to quadrants. So in this case, we have to completely solve one particular quadrant to get the values for the rest of the quadrants. Now, for circle, we need to plot only one octant, but for ellipse, we are going to plot an entire quadrant. So let's see how it works. So in this case, you can see in the case of circle, we had just drawn this particular like graph, right? So here you can see here we have two parts, right? So this is the part when we start from the top, okay, from the y-axis, and then we finally reach to the x-axis. So this is one entire quadrant. Now in this entire quadrant, we divide this particular quadrant into two regions, region 1 and region 2. So the what is the breakpoint of this region? We have Q, which is the breakpoint, and we can say that the region 1 or part 1 is the part wherein the slope is less than -1, and the region 2 is the part wherein the slope is greater than -1. So in this case, you can see that at the top in region 1 or part 1, you would say, you can see that x is going to increment with a unit distance of 1 every single time, but y is going to be the same as we did in the circle algorithm. So this is what the x will be going with respect to the unit distance, right? So this is part 1, and y obviously will have to again decide whether it chooses yk or yk minus 1 with respect to the position of the midpoint, right? But other way around in region 2, we can see that the x is not going to increment with unit size, wherein y is going to decrement with respect to unit size every single time. And we have to choose now between x, right? So again, we'll use a midpoint to choose which x coordinate we need to take into consideration. So if the midpoint is lying inside the ellipse, then we are going to choose xk. If the midpoint is going to lie outside the ellipse line, then we are going to choose xk plus 1. So this is how we decide. So now we are going to derive both the parts, that is part 1 and part 2, and accordingly we'll solve the equations. So now for quadrant 1, that is in quadrant 1, region 1, what is the starting point? So the starting point is obviously this particular point at the top, wherein we have x-axis as 0 and y-axis as the minor axis, that is r of y. So we start by 0 comma ry, and the slope of the curve is less than -1. Now we need to take unit steps in positive x direction till the boundary between the two regions is reached. What is the boundary? The boundary region is this q, wherein my slope is equal to -1. So as soon as we reach the slope equivalent to -1, or we reach a case wherein we go for a slope greater than -1, we need to stop. So let's understand how the slope equation works. We'll derive that thing also. And in case of region 2, obviously we don't know what is the starting point, because whatever would be the end point of region 1 would be the starting point for region 2. And as we go to the region 2, we know that the slope is going to be greater than -1, and then we'll take unit steps in the negative y direction till we reach the end of the quadrant. That means we'll be coming down by y-axis by unit size. Every time we'll be doing -1 till we reach where x is equal to rx, right? That is the major axis, and y is equivalent to 0 till we reach this point. So let's see how it works now. So we'll understand the slope. Now, what is the slope of an ellipse? To find the slope of an ellipse, we are going to use derivative on the equation of the ellipse. So here we are applying derivative dy by dx onto the equation of the ellipse, and we see that we take the y, which is a variable, okay, on the left hand side, and the rest we push it onto the right hand side. Now in this, dy by dx of y square equivalent to dy by dx of the rest of the items. Now in here again we can like divide this into two parts, wherein rx square can go with the left term and the rx square can go with the right hand term, and we have minus in between. Now we clearly know that rx, ry, and rx are what? Constants, because they are the minor and the major axis, right? So obviously the constant derivative, it's gone, but the derivative of the variable still remains. So we have the right answer, that is minus dy by dx of x square into ry square divided by x square. Now what is dy by dx? So finally, when we derive y square, it becomes 2y, and x square, when we use the derivative, it becomes 2x, and then we take 2y and bring it below on the right hand side, so it becomes minus 2x ry square divided by 2r square rx square y. So this is how we get the slope. This is the slope. Now we know that the slope at the boundary point between the two regions is -1. So this is the equation of the slope, which will equate it directly to -1. So if it equates to -1, what do we get? We get minus 2x ry square equivalent to minus 2 rx square y. So whenever the left hand side is equal to right hand side, we'll clearly say that we have reached a point wherein the region 1 ends. So the left hand side part should never be equal to the right hand part. It should be less at the start. Okay, slowly we'll see that the left hand side gradually increases, and the time it is equal, we got to stop, or if it is greater than the right hand side, we got to stop. So that is how we work. We'll look at it at the in the example section. Now, so let's start deriving the region 1. So what is the derivation for region 1? We all know region 1 looks like almost like the circle equation. So wherein we can see that this is the midpoint. This midpoint is going to help us choose whether the next point on y-axis, where will it be yk or yk minus 1. So we all clearly know the logic. The logic is that if the midpoint is lying inside the ellipse, that means ellipse is closer to the above point, right? So if it is closer to the upper point, we'll choose yk. If the midpoint is above the ellipse, right, outside the ellipse, that means the line of the ellipse will surely be closer to the below point, so we'll choose y next as yk minus 1, right? So now again we know we have these 2 points, xk plus 1 comma yk, that is this one, right? And the next point is xk plus 1 comma yk minus 1. So we can get the midpoint out of it. The midpoint is xk plus 1 comma yk minus half. Now what is the equation of an ellipse? We have this. So now we can directly place these values of xk plus 1 and yk minus half into the equation of ellipse, which we have done correctly over here, and that becomes our decision parameter. Now why we have written p1k? It is because we are solving the region 1. So this is the decision parameter for the region 1. Similarly, as we did it for the circle, we'll find out next decision parameter, that is p next. So this is p1 k plus 1, and to do that we are just replacing k with k plus 1. You can clearly see that happening right now. So we can see that pk plus 1 equivalent to, we can write xk plus 1 as xk plus 1. Why is it so? Because we clearly know that when we are in the region 1, the x next is always going to be xk plus 1. As you can clearly see over here, xk gets incremented by 1. So xk plus 1 is going to be xk plus 1, right? So I've just written this particular term as xk plus 1. Okay. Now, obviously, we are going to derive the next decision parameter with the help of the previous decision parameter. So, we are going to find the difference between the two so that we have a relation between the two. So, we'll be doing p1k plus 1 minus p1k. So, when we do that, this is what is the equation. This is how it looks like. So, obviously, I've written all the x terms together, the y terms together, and rx square y square, ry square plus rx square ry square. So these two terms, obviously, they are going to cancel each other off as they have different signs. Now I'm going to open up all the a plus b whole square things, and surely we see that we have ry square, which is common, which is outside. Similarly, over here we have rx square term, which is common. We take it outside. We try to solve the equation. After solving it, we slowly derive and we reach a point wherein we have the difference. So the difference looks like p1k plus 1 minus p1k equal to, okay, this particular equation that we just derived. Okay, now in this equation we see that what is xk plus 1? Xk plus 1 can be written as xk plus 1 because obviously x is going to increment by unit distance. Okay, but can we do that for yk plus 1? We can't, because yk plus 1, we have no surety whether it's going to be yk plus 1 or it's going to be yk. So that's why you can clearly see that this xk plus 1 got changed into x of k plus 1, and this yk plus 1, we had no clue to what we can change it into. That's why we have just left it as it is, because we are still unsure whether it would be yk plus 1 or yk. So these decisions we need to take now. Now, so let's start with the derivation. So let's see what happens in the derivation. Now, we clearly know if P1k is less than 0, it means that the point lie inside the ellipse, and obviously for next y we need to choose yk. But if the midpoint lies outside, we surely know that the next yk we are going to choose is yk of minus 1. Now, so what happens then? So we can directly write if P1k is less than 0, the y doesn't changes. So instead of yk plus 1, we can write yk. So everywhere you can see wherever we have yk plus 1, we have written yk. When we do that, we have to see that they have different signs and they directly get eliminated. So we have no right hand side over here. So we are left with only p1 k plus 1 equal to p1 of k plus, we expand this part, so ry square gets multiplied with 2x of k plus 1, plus we have this ry square separately. So this is what we get. Now similarly, when we proceed and we see if p1k is greater than equal to 0, that means the point lies outside. So obviously the next y would be what? So the next y is yk minus 1. So now we replace yk plus 1 as yk minus 1 wherever we see y of k plus 1. So when we do that, we have to expand this. When we expand this, most of the terms get eliminated. And finally, what we have is 2yk plus 2. This 2yk plus 2, I can remove 2 outside, right? And when I remove outside, it looks like yk minus 1, which is what? It is what? Y next. So we clearly know that yk minus 1 is what? Y next. So we can directly write it as yk plus 1. So this is how we get the decision parameter in case the point lies outside or on the circle, we can say. Okay, or sorry, on the ellipse. Now this is the decision parameter. Now we can find out the initial decision parameter, that is p10. To do that, we have p1k. This formula is already there with us. We just need to replace it by 0 comma ry. What is 0? Because at the start, if we look at the ellipse, this point is going to be what? X is 0 and y as ry. So this is what we are going to replace in this particular equation. And finally, what we get is p10 as ry square minus rx square ry plus 1/4 of rx square. So that is it. Now let's derive the region 2. Now, to start with the derivation of region 2, we need to know where to start and what is the starting point. So we all know that we need to start when the slope changes from less than -1 to equal to -1 or greater than -1. So this is the point wherein that will be the start of region 2. And how will we get this point? It will be the end point of region 1 that we'll be getting, and that will be using as the starting point for region 2, right? So let's see how that works. So now we clearly know that when we start the derivation for region 2, the starting point is the last point of region 1, and we clearly know as we come down, the slope is going to be different, right? So in this case, the y is going to be decrementing by unit size every single time, wherein the deviation in x is not going to be much. It's not going to be of unit size. So what is it going to be? Obviously, it's going to be less than unit size. That's why we need to decide whether the next x, that is x next, whether it's going to be xk plus 1 or it's going to be just xk. So that again can be decided with the help of the midpoint. If the midpoint lies inside the ellipse, that means the arc of the ellipse is closer to the outside pixel. So if it is closer to the outside pixel, so the value could be taken as xk plus 1. But if the midpoint is outside the arc of the ellipse, that means the arc of the ellipse is inside, then we'll have to clearly say that the value of x doesn't changes, and we need to plot the pixel as this pixel, so xk remain as it is. So let's get started. Now in this case, what is going to be the midpoint? So we clearly see that the midpoint is xk comma yk minus 1, that is this point, and this point, that is xk plus 1 comma yk minus 1. So between these two we need to decide now. So what would be the midpoint? We just need to add them up. So as we add it up, we get the midpoint of xk plus 1 by 2. Okay, we add and we divide by 2 for surely. So, and yk is what? 2 times yk minus 1, so that becomes what? Just yk minus 1. Now this is the equation of the ellipse, and now we're going to find out the decision parameter for the region 2, that is p2 of k. So in the equation, we are just going to replace the x value and the y value of the midpoints. As we do that, the equation looks something like this. Similarly, we find for the decision parameter, that is the next decision parameter, because that is dependent on the current. To make it dependent on the current one, we first write the decision parameter. When we write it, we see that we replace just xk with xk plus 1 and yk with yk plus 1. But now we know what is yk plus 1. It is going to change by unit size and it's going to decrement by unit size. So we can write yk minus plus 1 as yk of minus 1. So this is the p2k plus 1. Now we need to have a relation between them. So we will divide this, we will subtract this so that there's a relation between two decision parameters. And the next decision parameter is dependent on the prior one. So let's see how it works out. So we are computing the difference over here. So we have written this is P2K, the X parts together, the Y parts together, and the constant parts together. So you can see the constants will get eliminated because they have just opposite signs. The rest is the same. When we start expanding this particular equation, this is a plus b the whole square kind of thing. This is again a plus b the whole square. Similarly, this is a minus b the whole square. That is what we are expanding, and this is the same, a minus b the whole square. So when we expand this, we take the ry square terms together, that is outside over here. Similarly, for this entire thing, we take rx square terms together, which is here, and then we expand. When we expand, we get something like this. On the left hand side, we have xk plus 1 the whole square plus uh, xk plus 1 minus xk square minus xk. But on the right hand side, a few of the elements gets deleted, just like minus 2yk plus 2yk. Okay, many terms get deleted, and finally what we have is minus of 2yk plus 2 plus 1. So this 2 I can take it out, which would look like minus 2 of yk minus 1. We all know what is yk minus 1. It is y next. And what is y next written as? It is written as y of k plus 1. So we can clearly rewrite this as 1 minus 2 times of yk plus 1. So this is the difference now. Using this difference, we can find out the decisions, right? So now this is the same thing written over here as yk minus 1 can be represented as yk plus 1, right? But obviously for xk plus 1, we have nothing to be written because we don't know whether it's going to be xk plus 1 or x of k. So now deriving the decision making part. So let's see how we are going to work it out. So in this case, we have p2k plus 1. I've just taken this particular term on the right hand side, that becomes positive. So this is how it looks like. Now I'm going to use the point, okay, where it lies, and I'm going to replace the values inside the decision parameters, right? So if p2k is greater than 0, that means the point midpoint lies outside the ellipse. If it resides outside the ellipse, that means this arc will be closer to xk and not xk plus 1. So xk is not going to change. So we can write xk plus 1. This is x next equal to xk. So I'm just going to replace that. When I replace that, of terms gets eliminated right away. Finally, what I'm left with is just p2k plus 1 equal to p2k minus 2y of k plus 1 rx square plus rx square. So this is what is left. Similarly, when I solve for the other part wherein the point lies inside, right, it is less than or equal to 0. So that means the xk term, right, has to be incremented. That means the arc is closer to the next pixel, so xk will be replaced by xk plus 1. So that is what we do. We replace xk by xk plus 1 in this particular equation, which is here. Once we do that, we try solving it. After solving it, okay, most of the terms get eliminated again. Finally, what we are left with is p2k plus 1 equal to p2k plus 2 ry square x of k plus 1 minus 2y of k plus 1 rx square plus rx square. So this is what comes out of it. Now, so the region 2 derivation is also done. Now we need to find out just the initial decision parameter for region 2. But to find out the initial decision parameter for region 2, do we have the initial point for region 2? No, that is what we are going to get from the region 1. So obviously we can't put in anything over here. So we just take some arbitrary point x comma y and we just put it into the equation of p20. So it's xk is just replaced by x and yk is replaced by y. So this is how we get the derivations, and let's get started with the solution. So to understand the solution, now how do we get started? We have two radii, Rx and Ry, and we have the starting point wherein x is equal to 0 and y equal to Ry, right? So now we are solving first the region. So we calculate P1 of 0. So we just replace the values of x and y inside this thing, okay? And that's how we get P1 0. Similarly, we have dx and dy, right? We have dx and dy that will be calculating throughout the way, and we know from the derivation that they shouldn't be equal, right? And dx should always be less than dy in region 1. If it goes above the dy, it means that we have crossed into region 2. So we will repeat this algorithm, right, till dx is less than dy. So we will see what is P10. If it is less than 0, then what does it mean? If it is less than 0, that means point lie inside the ellipse. That means this arc is going to choose the upper point. So in the upper point, y doesn't change, it's only x changes. So you can see x is changing from x to x plus 1. That is x next equal to xk plus 1. And y is nowhere changing. We calculate dx. We check because only x is changing. So we calculate dx and we verify whether this dx is still less than dy. Okay, plus this dx is dependent on the new value of x, that is x of k plus 1, right? And we also find the next decision parameter, that is p1 of k plus 1. We find that, and again we check whether that particular value is less than or greater than 0. If it is greater than 0, we'll execute the else part. In the else part, we clearly see that means the midpoint is lying outside the arc. If it is lying outside the arc, that means this arc is going to choose the below point. Below point means what? X is going to change from xk to xk plus 1, and yk is surely going to change from yk to yk minus 1. So you can see x is changing from xk to xk plus 1, yk is changing from yk to yk minus 1. And obviously in this case, as both are changing, we need to calculate both dx and dy. And again, we'll check whether dx is less than dy. If dx is less than dy, then we'll continue again. We'll calculate the next decision parameter using this particular value of decision parameter that we have derived before. We'll again go inside the if statement or the else statement, depending on what outcome comes out, right? We'll keep solving this until and unless dx is less than dy. As soon as we have dx equal to dy or greater than dy, we'll stop. And that's when we get our decision point for, the initial point for region 2. So that is the last point of region 1 and the starting point of region 2. So let's get started with region 2. In region 2, we clearly see that now the dx is not going to be less than dy. It's going to be greater than or equal to dy. So we calculate p to 0 with whatever point we get from region 1. So we calculate p to 0 and we check whether it is greater, right? Whether it's like greater than 0 or less than 0. So if it is greater than 0, that means the point lies where? It is lying outside, right? The midpoint is lying outside the arc. If it is lying outside the arc, then the arc has to choose this particular point. Then this point x doesn't change, y changes to yk minus 1. So you can clearly see x doesn't change, y changes to y minus 1. That is what is represented. We calculate dy, and finally we calculate the next decision parameter as derived. And again we check whether it is greater than 0 or less than 0. If it is less than 0, it means that the point lies inside. So this arc has to choose the point which is to the right hand side. In this case, x changes to xk plus 1 and y changes by minus 1. So you can see x changes by plus 1, y changes by minus 1. In this case, we have to calculate both dx and dy, and then finally we have to find the next decision parameter. But let me tell you, now do you feel dx and dy is of any importance to us? The thing is, it is not of importance because now we know that we are going towards the x-axis. That means we are going to keep on doing this, okay, till we have the ending condition. And what is the ending condition for region 2? The ending condition for region 2 is that the y value, okay, it goes to 0. That means we have reached the x-axis, right? The line, x line. Okay, so the y we are trying to reach, we are reaching, and when y is 0, we have reached the x-axis. So that is how we have the ending condition. So we need not determine it with the help of dx and dy. Dx and dy were just needed for region 1 because that was with respect to the slope, and we were calculating it so that dx is less than dy, so that the slope remains below minus 1. Now, so this is it, and let's move on to the example. So we'll solve an example and we'll be more clearer of how to go about it. So here is the example. In the example, we clearly see that we have the semi-major axis as 8 and semi-minor axis as 6. And we have the initial point which is starting from 0, 6. So why it is 6? Because ry is 6 and the initial x point is 0. So this is the initial point. Using this, what do we calculate? We calculate P10. So we have already seen what is P10. So to calculate P10, let's go and check what is the formula. So we know in region 1, P10 is just ry square minus rx square ry plus 1/4 of rx square. So using this formula, we are going to calculate P10, and that comes out to be minus 332, right? So now we have minus 332. So using P10, we see whether it is less than 0 or greater than 0. As it is less than 0, that means the midpoint lies inside the ellipse. So if midpoint lies inside the ellipse, so in this case, can we increment y? No, we can't increment y, right? Because it will be choosing the upper point, wherein the x will surely be incrementing. So x goes from xk to xk plus 1. Y doesn't go below, it just remains at yk. So you can see x getting incremented. As x increments, we calculate only dx. Similarly, we find the next decision parameter, that is pk plus 1. So after calculating all of this, when we try pk plus 1, we get the map value as minus 224. So we see the calculation of dx now. Dx is for 2 into xk plus 1 ry square. So you know ry square is 6 square and xk plus 1 is this one that we have just derived, and so we get the value 72. And the y doesn't change, so y is dependent on rx square. So you can see this is the major axis, the square into y is just 6, which has not changed, which comes up to 768. Similarly, we go and we see that as we have derived minus 224, it is less than 0. If it is less than 0, we come into this if statement again, and we see we only increment x and we don't increment y, because we again choose the upper y, okay, and x surely has to increment. So in this case, the point is lying inside the ellipse. So you can see x has incremented. As x has incremented, we calculate dx. What is dx coming up to? It is just changing this 1 into 2, right, and it becomes 144. As y doesn't change, the dy doesn't change. Using this, we calculate the next decision parameter, that is pk plus 1, and we get the next pk plus 1 as minus 44. As we get it as minus 44, we again go to this if statement, and in this if statement, we again know y doesn't increment, only x increments, so x goes from 2 to 3, y remains the same. We calculate dx, okay, wherein only this variable changes to 3, and we get the value as 216, wherein y remains the same at 768. Using this particular values, we calculate the next pk plus 1, and the next pk plus 1 comes up to be positive. So as this pk plus 1 is positive, we go to the else part. And the else part, as it is positive, that means the point is lying outside the ellipse. It is lying outside the ellipse. In that case, we choose xk as xk plus 1, but y is surely coming down. So it is yk minus 1. As it is yk minus 1, right? So you can see x has got incremented by 1, y has got incremented by 1. We need to calculate both dx and dy. So now we can see this value has changed to 4 and this becomes 288. And in this case, y has changed from 6 to 5. So the value decreases from 768 to 640, right? Now using this x and y, surely we calculate the next pk plus 1 using this formula. And when we do that, we get the value as minus 108. As we get minus 108, we again go into less than 0 side. In this if statement, we only increment x. There's no increment of y. So you can clearly see the x is incrementing from 4 to 5. Y remains the same. So we calculate only dx, which we get as 360. Y remains same as 640. Using this xk plus 1 and yk plus 1, we calculate the new pk plus 1, which comes out to be 288, which is positive. As it is positive, x increments and y decrements. So obviously 5 comes to 6 and y changes from 5 to 4. So we calculate both dx and dy, and surely we can see both the values are coming nearer, right? They are coming closer. Like, and again we see that when we calculate the new pk plus 1 using 6 and 4, right, it comes out to be 244. When it comes out to be 244, it is again greater than 0. So we again increment the value of x and decrement the value of y. So we see it is 7 and 3. And now when we calculate dx and dy, we see that for the first time the dx has gone above dy. So in this case, we got to stop now because the condition says that y dx is less than dy, I need to continue. So this is the end point for region 1. Now this end point can be used as the starting point for region 2. But for region 2, first we need to calculate the initial decision parameter, that is P20. So to calculate that, we will just look at this formula, right? P20 is what? X plus half the whole square ry square plus y minus 1 the whole square rx square minus rx square into ry square. Now we take 7 and 3, so that is the initial point for region 2, and we set it into that formula. When we do that, we get P2k. It's not P1k, it is P2k. So we get P2k as minus 23. As it is less than 0, we say that in this case, the point is lying inside the ellipse. So inside the ellipse, that means obviously my x should be incrementing, right? We'll be choosing the right hand side pixel. Okay, you can see that happening over here, right? As it is inside, right, we have to choose the next x, that is xk plus 1. And obviously y is going to decrement for sure in region 2 every single time. So the y, you can see it was 3 initial point, which has gone down to 2, and you can see the x is surely taking the right hand side point and it is coming to 8, right? So now using this, do we need to calculate dx and dy now? Surely no, because obviously that is not going to help us as we have crossed the slope of minus 1 now. We just need to stop only when y is equal to 0. So let's calculate the next point, but for the next point, we see how do we calculate it? We use 8 and 2. We use 8 and 2 that we have just got, and we calculate the next P2 k plus 1. So next P2 k plus 1 is computed using what? X plus 1 and y plus 1, that is 8 comma 2. When we do that, we get the value as 361. When we get value as 361, we know it is greater than 0. Again, what we need to do? We need to what? Increment the value, as it is greater than 0, we clearly see if that means the midpoint is lying outside. So that means the arc has to choose the same xk, right? And the yk is obviously going to decrement by 1. So in that case, you can see the x doesn't increment at all. It chooses the same xk and the y decrements, right? So using this new xk plus 1 and yk plus 1, I put it into the same equation of P2 k plus 1. When I do that, I get the next P2k plus 1 as 297, which is again greater than 0. If it is greater than 0, I need to again see that the point is lying, midpoint is lying outside the arc. So arc need to choose the left hand side point, which is xk, and y will surely decrement by 1. So obviously x is remaining the same and y is coming to 0. As the y came to 0, we know that is the stopping condition because y need to be greater than 0. So as we have that, we can see the plotting done for the first quadrant. Okay, so how do we do the plotting? We start from 0, 6. So you can see 0, 6 isn't plotted. Then we have 1, 6, this point. 1 comma 6, then we have 2 comma 6 which is plotted over here, then we have 3 comma 6 which is plotted over here, then we have 4 comma 5 which comes here, then we have 5 comma 5 which comes here, right? Then we have 6 comma 4 which comes here, and then we have 7 comma 3 which comes here. So this is the endpoint for region 1. Now this becomes the starting point for region 2. So for the starting point for region 2, this is the same. And from that starting point, we get the next point as 8 comma 2, so which is this, right? Then we get 8 comma 1, which is this, and then we got 8 comma 0, which is this. So using this, we can get the values for quadrant 2 as well. If we go in the similar way like this, then we have this, we have again this, we have this, then this, right? And so it would look something like this. The region 2 would look something like this, right? So this is how we get, sorry, not region 2, it is quadrant 2. So it will look something like this. Hope you have understood. Uh, we can just plot it one above, right? And this would be something like this, right? So it would look something like this. So I hope it is pretty clear. You have got the example, and this is how we solve the entire quadrant using one entire quadrant. Using the symmetric property of ellipse, we make the second quadrant. Then we have one half of the ellipse completely. Using one half, we can get the other half, right? So I hope you have enjoyed the lecture. You understood the derivation and the example as well. If you have liked the video, kindly like, share, and subscribe. Thank you for watching the video. Happy learning. Enjoy computer graphics. Thank you.